everyone. Today we're going to be going over a linear algebra theorem, and this theorem basically states that if you have a coefficient matrix of A of variables x, and the dot product equals 0, thus it's a homogeneous system. Any non-trivial solution to said system Sn, that solution Sn, that's non-trivial, it's going to be orthogonal to the rows of the coefficient vectors. And we're going to prove this and then show an example to kind of solidify the proof. But basically, what this is looking like is if we have in 3 space, okay, and we have some vectors, let's say, these here, the rows, the individual rows. So I'm not going to use real values, but let's assume that we have some vector like this, and some vector maybe like this. This is row 1, right? So that would be this guy here of this matrix C. Let's call this R2. That would be this guy. They're not real values again, but just assume that they are. And even maybe this is R3 here, and this would be this row. And what this says is that if the dot product, if a solution, if the dot product between the coefficients and the variables is 0, then the solution vector that you get out of that, the values for x1, x2, x3, xn, in this case just x1, x2, x3, they're going to be mutually orthogonal such that you have right angles with all of the individual vectors that you're looking at. So let's go ahead and prove that. So imagine you have some system in the homogeneous form like this. Well, it turns out that you can actually look at this homogeneous system as a series of dot products. If you notice here, this is a dot product, and it's specifically a dot product of some vector A dotted with some vector x, right? And if you hopefully you can see that, right? This is if this vector is A1, A2, A3, right? Well, this is just dotted with x1, x2, and x3, right? And we're basically saying that the system must equal 0. So this linear system, whatever this dot product is, equals 0. But what do we know about a dot product that's 0? Well, recall that some vector, let's say vector A dot B, right? We know by the cosine identity of this, it's going to be cosine of theta times their magnitudes. And I won't get into proving that, but you've seen this before. Well, if this equals 0 and the magnitudes are non-zero, so these are not 0, well then cosine of theta must be 0, and the only way to get cosine of to be 0 is if theta equals 90. So this condition is only true such that the dot product is 0 if and only if the theta between the vectors is 0, or sorry, is 90 degrees. And that's what this is showing here, right? You've seen this before. If a vector, if the angle between two vectors is 90 degrees, then their dot products are 0. You've seen that. So in this case, the homogeneous system is equal to 0. So, and notice these are, if we put this in a matrix C, A1, A2, A3, yada, 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 right? Well, what this is saying is that if we have any system in this form, right, that would look something like this. If this is equal to 0, well, if we row reduce echelon form down and get functions of x, or sorry, we get a solution that's not trivial. So there's a solution here, and you can find that many ways, I'm sure you know. Well, then that solution, which we'll call S1, S2, and S3, so that's a vector, is perpendicular to the row vectors, which in this case, if we take row 1, for example, that's going to be A1, A2, A3, and it's actually perpendicular to all the other ones. So it's perpendicular to this vector. It's also perpendicular to the next row, which would be A4, A5, and A6. Okay, and even the last row too, right? And hopefully you see that because the dot products are 0. That's the whole point. It's actually a really simple theorem once you just kind of look at it as a dot product. All right, so the vectors, they're all orthogonal, or the solution vector is orthogonal to the 3. That's not to say that the row vectors themselves are orthogonal, so avoid that mistake. They're not orthogonal themselves. That's why I'm denoting that the solution set is orthogonal to the 3 row vectors respectively. And this is true in any Rn space. So this theorem holds for all Rn. Draw a little smiley face. So let's work an example just to show that this is true. So assume that A is some vector, which we have here with the coefficients of 1, 2, 3, 4, 5, 6, 5, 7, 9, and the solution set to this, and assume that this is equal to some vector B, which is homogeneous. So it's equal to 0, 0, 0. And the solution set is this guy here. So 1, negative 2, 1. Well, let's plug in each row vector. So let's call R1 a simple vector of 1, 2, 3. Let's call another another row vector 4, 5, 6. And the final row vector is 5, 7, 9. And if you were to plug these solution values into this system, you would see you'd get 0. So that means that the dot product is 0. And if we go to my Desmos here, sorry, I used ChatGPT to get this nice example. In red here, I have my I have the vector itself, right? The solution vector. So the solution vector is pointing to 1, negative 2, 1, which you can see here. But if we then look at R1, we see a 90-degree angle. So that of course means that the dot product will be 0, and you can prove that quite simply. If we look at R2, again, 90-degree angle, orthogonal, and orthogonal to the last row vector. And if you superimpose all of them, or not superimpose, show all of them at the same time, you'll see that they are all mutual, or the solution vector is orthogonal to all 3 simultaneously. So that's just some geometry of a linear system that might be a little helpful. So hopefully you can see it here, and have a wonderful day, guys. Bye-bye.